Okay, we'll go ahead and get started here. Again, welcome to the final presentation of Applied Day 2021. I'm joined today by Matti Kariluoma for his presentation on embedded systems. You'll hear from him in just a minute here. Before we dive in, I just want to give a quick background on applied engineering. For over 35 years, Applied has been helping companies overcome their engineering challenges, whether that be with our technology team providing training, implementation, and support for software and hardware solutions, or our services team providing design and manufacturing engineering, as well as software development and reprographics. Applied fits your needs. With that, I will turn things over to Matti.
Hi there, everyone. I've been asked to give a presentation on embedded systems and the technologies and common tasks that we are solving for our customers when they come to us with a problem. So to start things off, we'll talk about what embedded systems are. It's usually a software development sort of task, but it has to do with physical devices out in the world rather than something that's web-based. So to start it off, whenever people ask me about my work and what I do, something that's very easy for us all to connect on is to discuss the technologies that we interact with in our daily commutes in our cars, and how most of the technology has moved towards touchscreens in cars in recent days, and then also the smartphone in your pocket. These would be considered physical devices that the user has to interact with, and as part of what embedded engineers do is they make these user interfaces that take human input and put them into a machine and make them robust, reliable, make it easier for the application developers that will later write software on top of the hardware, make it so that they can interact with or respond to the user's gestures. So what's nice about touch screens is, especially since now that Apple has popularized the capacitive style touchscreen, it makes it so that you can have user interfaces that are suited for the task only. It really reduces the cost of the overall device, and that is why we see it in cars. Before, if you wanted to have a radio interface, and then if somebody wanted to put in a CD and listen to a CD, all of the buttons all of a sudden start doing different things. So instead of it being radio presets on the 5 buttons below, it becomes fast forward or next track, and that can be confusing to users. One other benefit of touchscreens is it makes it easier to keep moisture and dirt outside of the electronics, as we've seen with smartphones going from 2010 up to today. They've started to remove some of the external ports going into them. And so while there are a lot of benefits to going to a touchscreen, mostly a user interface that can change on the fly and better better protection from the elements, there also is the downside of you have to look at the screen. You can't really use these interfaces without looking at them. Again, why I always go to talk about when you're driving a car, it can frustrate users that the touchscreen there in the center console, not only is it on and bright and it's distracting them while they're driving, if they want to change the radio station, they have to take their eyes off the road to do it. So another part of an embedded software developer's job is to deal with the various types of switches, joysticks, and buttons, and how to respond to the input on these things. For instance, buttons typically don't just give a clean signal to a microcontroller when somebody presses on a button. You need to know to debounce that signal so that you don't have a bunch of user inputs being commanded over and over again. You need to smooth out that response and wait a while and let things settle down before you react to it. And then this is where, since it's only typically embedded engineers that deal with these sorts of devices, they also get asked engineering questions, mechanical engineering questions about them too, about, well, which joystick should I choose? And, is IP66 waterproof, water splash rating good enough, or do I need to go to IP67? And so an embedded engineer's task can become to go onto a supplier's website and help the customer define the requirements and pick out a physical user interface, such as a joystick for the customer's application. Again, keeping on the same task of user input, it's become very popular now to have a physical user device that is wirelessly connected to the device that you're talking to. In this picture example here, I'm showing a unmanned aerial vehicle, but it can be as simple as just a button that when you press it, it changes the state of some machine across the room without having to have a physical cable connecting you and the machine, either for ease of operation or reducing tripping hazards. And so we will talk to the customer about the requirements and what are the trade-offs for using the different wireless technologies, such as Bluetooth, which is very simple in operation, but very complex to acquire the components for. Wireless internet, Wi-Fi, is also very popular and very commodity. And then as you get into more real-time or more safety requirements, you'll start to look at point-to-point radios, and then you'll start having to talk about antennas and the different spectrums that are available for use. As I touched on when we were talking about physical user interfaces, it turns out that not a large portion, but we are often consulted on how to help design these systems so that they can withstand being exposed to the elements. And then in our own work product, our software that we write that helps to decode the input that the user is giving, we need to be aware of the outside environment. Oftentimes there will be a temperature sensor on one of our devices, and we will reference that when we are trying to decide what this input means. Did the user press this button, or is this just something else? And the big four are listed here. First of all, sunlight. Not only can it degrade the components such as rubbers and plastics that are used to keep the other elements out. It can the sun rising up in the morning has a very, very large effect on electronics. It's surprising. You would think that from one day to the next, it's 80 degrees Fahrenheit, 100 degrees Fahrenheit. You'd think that that would be what you're trying to design for, but in fact, it's the night-day cycle where as the sun is rising, anything that you have outside will go from whatever its resting temperature was all the way up to its maximum temperature for the day there in a very quick amount of time. And so not only do you need to be able to work over a range of temperatures, you also need to be able to work with a large gradient in temperature that happens very quickly. One thing that we are familiar with in this area of the nation is freezing temperatures and what it can do to infrastructure. Just something, I guess, to motivate why we would be too worried or not about moisture getting into the things that we're working with. And then something that is sometimes surprising to customers is how the newer technologies for batteries react to freezing temperatures. For instance, lithium-ion batteries in your cell phone, they will not only shut down when they're overheating, but they will go into a safety shutdown mode when they are too cold to operate. And that is not too cold. It's about 20 degrees Fahrenheit, I think, for personal cell phones, which you don't typically see until you have some sort of a test environment that you're trying to work with, where you have sensors that are cell phones out collecting data, and they're just sitting on a table in a cold room, and you're wondering why they're shutting down even though they're plugged in. So not only the sunlight causing things to heat up and frigid temperatures causing things to cool down, and the sort of mechanical things that those can do to devices when they shrink and grow. Moisture, especially moisture in environments where there is salt. Not that the embedded engineers would be too concerned about doing anything about these. It's just something that they need to have in their mind when they are designing or helping to design the user interfaces, or when they are testing these user interfaces after they have successfully built a prototype and now they're testing to see whether it works, and especially whether it works reliably. The application developers that rely on our work output don't really want to be dealing with the hardware just going off and acting on its own. They want to have a very reliable base system that just handles all the complexities of dealing with the real world and turns it into stable logic that the application developer can then depend upon. So besides temperature and moisture, in some environments, you have to worry about dust, especially fine dust, as it can work its way inside of enclosures, and then a lot like moisture, where it can short out components, but dust will make it difficult for these, especially buttons and joysticks, where they will lose their sensitivity or they will no longer give a signal when they are being activated. And I guess that touches again on engineering and testing these devices to make sure that they are reliable, so that if, for instance, the customer's requirements are something like, I want this button to turn off this machine if it's pressed, sort of like a safety e-stop, then these are the sorts of concerns that would have to be looked at and tested against, and just to be kept in mind. And again, to go back to the first slide about the physical user interface, that's another reason why touchscreens are becoming much more popular, because if you use some manufacturer's tested touchscreen interface, then you don't really need to worry about the effects of moisture and dust on them, because all you have to do is just wipe off the touchscreen, and then it goes back to operating the way it was before. And there's no internal components to wonder about whether they had been damaged, because just the only component that you can see is the screen right in front of you. And so usually the goal of what an embedded engineer is trying to do is to get robust measurement and reporting. And it's often because our systems are being used as input to automated systems. And there's a saying, garbage in, garbage out. If you don't have well filtered data being used as input into these systems, then it becomes very hard to reason with the system. It becomes very difficult for any further systems that are, what am I trying to say? Oh, no. It becomes very difficult to, because not only do the embedded engineers deal with the raw input and try to turn it into something that's a little bit more readable, so that the application developer can later take that data and use it. Sometimes we are filtering raw data into a signal that the embedded engineer himself is going to be using to further filter other raw sources of input. For instance, I mentioned earlier, sometimes we have temperature sensors on our products, and we're not trying to measure the temperature and give it back to the user or the application developer. We're using that temperature to understand how will some of our devices on this board react, knowing that, it's 100 degrees Celsius, knowing that these devices such as potentiometers or switches are going to react a little bit differently now that the temperature is a little bit higher. And so it's very important that you really understand what is the physical phenomena that you are measuring, so that you can correctly filter the inputs that you're getting from the electrical signals that are being sent through these devices to your microcontroller, so that you can give a final clean signal to not only the other systems that you have on your board, so that those can be used to, I guess, aggregate data, aggregate inputs into better, to help the application developer not be confused why, it seems like their device is failing at their code is failing at random, when it is just something like the code works at 40 degrees Fahrenheit, but it doesn't work when it gets over 100 degrees Fahrenheit. It's a sort of hardware bugs that are just impossible for application developers to figure out, which is why the embedded systems engineers usually take that sort of task onto themselves. Not only do we want to robustly measure the physical environment, but typically it is too complicated to talk about getting that data off of the sensor network and to someplace where the application developer can use it. And so in recent years, we've been tasked with a lot of with the work of integrating some sort of a wireless or cellular network onto the device itself, so that the report of this data is more automated. And so I've sort of switched topics here from physical user interfaces that a human operator is touching to more automated remote sensor networks, such as a soil sensor out in the middle of a agricultural field, and how that data gets off of that sensor after it has been robustly filtered, and we're pretty sure that we are measuring what we think we are measuring. And now that we have that data, how do we get it off of that device and to a place where an application developer can use that data to help the customer? And so while radio point-to-point networks have been used in the past and have very long distances, up to kilometers of distance, it's more and more becoming a requirement that you are just on the cellular network, such as Verizon, and you're just able to upload your data to some sort of application server somewhere. And so that's getting more away from embedded and engineering concerns and getting more into the software world, where now you're dealing with, well, first of all, you're dealing with cellular networks and SIM cards and how do you get on them and data plans and things like that. But then you're getting up to, well, now I need to have this device that's very rudimentary, that's only really measuring, some electrical signals from various sensors on it at a very low level of programming. And then you have to get it to a higher level of programming language on the same chip that can then talk to web services and send data out to them and negotiate these sorts of very complicated and very, very, I guess, verbose software stacks, such as the Internet Protocol. So switching topics again, first we talked about physical user interfaces that a user or operator would touch and directly manipulate. And then we talked about sensor systems where they are electrical, mechanical systems that are out in the field somewhere collecting data and reporting it. Another concern, another task that we are given by different customers is commanding motion. So instead of the user making a change to something physical and us reacting to that, we are now receiving commands from either another automated system or from the user through some sort of interface that an application developer has made. And now that we are sure we know what the user wants, we need to command some system to either move, or whether it be the engine in a car or some sort of a linear actuator that is moving something, or a pump to turn on and move some water or chemical into a vat. And typically, what customers use is the CAN communication networks, or what is it, controller area network. And so these will be used to control assembly lines. These are used to control automobiles, farm equipment. And so a CAN network is typically a fixed asset sort of network. So for instance, this example of in a car, the CAN network is physical pairs of twisted wire pairs that are wired point to point between each of the devices that are in the car. And so as an electrical engineer, it's not like routing on the internet where you have data in a packet and it's going wherever it's. When you're dealing with a CAN network, it's much more of an embedded systems task, where you have a device and it is connected to some other number of devices on a CAN bus, and you need to deal with the low level sending of, or programming the CAN controller to send the information out to the other devices, and then handle the incoming messages and what to do about that. So beyond how we command motion and the actuator that we use to command motion, another common task is either a system that already is moving, such as a centrifuge, I guess, where it's being operated by some other system. But now that we want to put some level of automation or measuring and reporting into the system, now we need to verify that this device is moving and at what rate that it's moving at. And so a common task is to attach some sort of, in this picture here, this is a rotary encoder, where you just attach it to whatever is moving, and then you can sense how much it has moved from 0 to 360 degrees and at what rate it's moving at. And there are many ways to verify motion. You can use electromechanical systems to measure the displacement, like how far a piston has moved. For every type of motion, there are multiple types of sensors that can sense that motion. And it's the embedded engineer's job to be aware of these systems and be able to write not software drivers, to write interfaces in the embedded systems themselves that can, knowing the physical properties of the device. So for instance, if I were going to do the system pictured here for a customer, I would need to know the diameter of this disk and the space between each of these markings on here, so that I could write software that could then count these and then figure out how many degrees has the device turned and at what rate is it turning at. And that would be and after I cleaned and filtered that data, that would then be what the application developer would get to define their business logic on how do they react to these measurements. And because we are so close to the actuators and the sensors for the actuators, sometimes we are also asked to do the control logic for these systems. And so, since we know or are very familiar with how we are measuring and what we are measuring, it's sometimes easier for the embedded engineer to go ahead and write the control logic for it, because the customer has a very high level requirement of, I want it to spin this centrifuge until it's separated the wheat from the chaff. And they don't want to write a control loop that is using a measurement of, well, how fast is it spinning, and what's the weight and this kind of thing. They just want somebody to do that step for them. And so the control loop would be baked into the measurement and reporting system, so that the application developer would be able to program the system at an even higher level of abstraction. And then finally, what I wanted to talk about was the idea. A lot of customers come to us with a device that they have prototyped and they've got working on their bench, or cobbled together in a large box of wires, and they want to start talking about, how do I take this prototype of mine that works but not very well and turn it into a sleek product for consumers or for other businesses to purchase. And typically the first thing that comes to customers' minds is they want to reduce costs and get it down to a printed circuit board. And so typically when you take apart a consumer device or something that you can buy at a big box store, this is what has happened. The manufacturer has taken their device and integrated all of the components onto one circuit board, and they've embedded that circuit board into the product, and it's just the cheapest way to manufacture items in large quantities. And that's typically all we see when we go to big box stores, is items that have been mass produced. But the problem with taking a device that you have developed yourself as a prototype and now that you want to sell is that you run right away into the problem of needing some sort of a regulatory agency, such as underwriter laboratories certification, and you also need to get FCC certification to sell to consumers. A lot of customers think that they don't need these certifications, but if you want to go the route of a printed circuit board, that usually means that you want to sell tens of thousands of units. And if you want to sell that many units, you probably do need to get your product into larger stores. You can't just sell them all yourself out of like a web store that you are running. And in order for other retailers to carry your product, they usually demand some sort of a UL or a organization like UL to certify your device to be safe. Another concern is FCC certification. If you have a product that is emitting radio waves intentionally, then you obviously, of course, need to have the Federal Communication, the FCC certification, whatever. But what many people don't realize is that you also need to have FCC certification for transmitters that you have on your device that aren't meant to be transmitting. Now, this isn't a concern for manufacturers of products that have no electrical control interfaces or anything. But embedded engineers, we are almost always dealing with some sort of a circuit board somewhere. And just because your circuit is controlling things and you don't have any antennas or anything on there, it's not good enough. You need to prove that you are also not unintentionally transmitting anything that can interfere with other devices. So you still need to go into a testing lab and have your device certified and verified that it is not unintentionally transmitting on other frequencies. And that can run up to the tens of thousands of dollars to have these tests done. And so for that reason, we often see or use in our own work a lot of commercial off-the-shelf components. One of the benefits of that is these have already been FCC certified and UL certified. And so you only really need to worry about the wires that you're using to run between these, or the system of the components that are put together. And so depending on what exactly it is you're trying to do, sometimes you can get a lot further cobbling together a lot of commercial off-the-shelf things rather than trying to go straight to a printed circuit board. So a level of complexity above just cobbling together a bunch of sensors and a bunch of electronics, mostly targeted at high schoolers or people just beginning their education. A lot of requirements can actually be met just by using a single board computer, where you go find something that has everything on the circuit board already, and usually many other things. For instance, this Raspberry Pi here probably has many interfaces such as HDMI and full internet and USB, that not every application will need to have all of these devices. But because this single board computer doesn't have anything hanging off of it, you won't be attaching anything to it besides, standard Ethernet or a standard USB. Then you can sidestep the need to have FCC certification almost entirely. And then going a step beyond a single board computer, you can use programmable logic controllers, PLCs, to do your automation work. These ones usually come with a much, you could say it's easier to program them, and you could also say it's harder to program them, but they are much more robust than single board computers. Single board computers usually have all sorts of failure states and software programming errors where they would either need to, well, for instance, on that Raspberry Pi, the operating system is stored on a SD card. Can't remember what that stands for. And so if it's subjected to vibrations, the single board computer will probably fail, and you'll have to reboot it in order to get it to back to a consistent state. Programmable logic controllers are usually much more robust, intended for automation on assembly lines and that kind of thing. So if you can get your requirements really baked down to exactly what you need, you can source a programmable logic controller and program that instead. And then it again meets all of the UL FCC certifications that you would otherwise need to go out and do yourself. All right, well, that's it. I guess that leaves us 15 minutes for questions.
Yeah, it doesn't look like there are any questions as of right now. Oh, here's one. What steps do you take to understand what a customer is looking for when it comes to embedded systems?
Well, you'd start with requirement solicitation, where you just ask them a series of questions to make sure that you're talking, because usually they have a very high level requirement. They want something to do this. And so you would maybe starting down with how does the data get into the system? So if a farmer comes and they want to have some system that is reacting to some sort of a condition out in their fields, before we talk about the actual device that they're going to be interacting with, we would talk about, well, how are they going to measure what's going on out there, and how is that data going to get transmitted back to some sort of a central authority that will then act on that. And then you would go on to talk about how do you want to tell the system to start and stop, and you just sort of build up the requirements from there on what's the environment, what are we measuring, and what does the user interface look like.
Yeah, and Maddie, if you don't have anything else, I think we'll wrap it up here. Again, thank you for joining us, and have a wonderful rest of your day.